Hey guys, and welcome back. Today we're going to be talking about an introduction to mechanical engineering, calculating gear ratios. Mechanical engineers must direct the correct amount of speed and torque to rotating parts in a mechanical system. Gear sets are one way of converting the rotational speed of an input shaft to a different speed for an output shaft. A gear ratio is the ratio of the speed, a regular angular velocity, of the input shaft to that of an output shaft. In a gear set, the speed at which a gear rotates is inversely proportional to the number of teeth on the gear. That is, the gear with more teeth turns more slowly than the gear with fewer teeth. Thus, the gear ratio can also be expressed as the ratio of the number of teeth on the driven gear, output shaft, to the number of teeth on the driven gear, or the input shaft. So when you are looking at a gear, you're going to start with a two-gear train. To be able to determine a gear ratio, you must have at least two gears engaged with each other. This is called a gear train. Usually the first gear is the drive gear attached to the motor shaft, and the second gear is the driven gear attached to the load shaft. There may also be a number of gears between these two that transmit power from the drive gear to the driven gear. These are called idler gears. For now, let's look at the gear train with only two gears in it. To be able to find the gear ratio, these gears have to be interacting with each other. In other words, their teeth need to be meshed and touching each other to be able to turn. For example purposes, let's say you have one small drive gear, which we're going to name as gear 1, turning a larger driven gear, which is going to be labeled as gear 2. Step 2 is to count the number of teeth on the drive gear. In this case, this is gear 1. One simple way to find the gear ratio between two interlocking gears is to compare the number of teeth, the little peg-like protrusions at the end of the wheel, that they both have. Start by determining how many teeth are on the drive gear. You could do this by counting manually or sometimes by checking for this information labeled on the gear itself. For example purposes, let's say that the smaller drive gear in our system has 20 teeth. Next, determine how many teeth are on the driven gear, exactly as you did before for the drive gear. So in our example, the driven gear is going to have 30 teeth. Now we're going to divide one teeth count by the other. Now that you have how many teeth are on each gear, you can find the gear ratio relatively simply. Divide the driven gear teeth by the drive gear teeth. In our example, dividing 30 teeth of the driven gear by the 20 teeth of the drive gear gets us 20 divided by 30 equals 1.5. And we can write this as either 3 divided by 2 or 1.5 semicolon 1. What does this gear ratio mean? It means that the smaller drive gear must turn 1.5 times to get the larger driven gear to make one complete turn. This makes sense. Since the driven gear is bigger, it will turn more slowly. So starting with a gear train or more than two gears, as the name suggests, a gear train can also be made of long sequence of gears, not just a single driver gear and a single driven gear. In these cases, the first gear remains the driver gear. The last gear remains the driven gear, and the ones in the middle become idler gears. These are often used to change the direction or rotation, or to connect two gears when directly gearing would make them unwieldy and not readily available. Let's say for our example purposes that the two gears train described above is now driven by a smaller 7-tooth gear. In this case, the 30-tooth gear remains the driven gear, and the 20-tooth gear, which was the driver before, is now an idler gear. So our next step is to divide the teeth numbers of the driven and the drive gears. The important thing to remember that when dealing with gear trains with more than two gears is that only the driver and the driven gears, usually the first and last ones, matter. In other words, the idler gears don't affect the gear ratio of the overall train. When you've identified your driven gear and driver gear, you can find the gear ratio exactly as before. In our example, we would find the gear ratio by dividing the 30 teeth of the driven gear by the 7 teeth of our new driver. So 30 divided by 7 comes out to 4.3. We would label this as 4.3 semicolon 1, and this means that the driver gear has to turn around 4.3 times to get as much larger driven gear to turn one time. If desired, you can also find the gear ratios for the intermediate gears. You can find the gear ratios involving the idler gears as well, and you may want to, in certain situations, do this. In these cases, start from the drive gear and work towards the load gear. Treat the preceding gear as if it were the drive gear as far as the next gear is concerned. Divide the number of teeth on each driven gear by the number of teeth on the drive gear for each interlocking set of gears to calculate the intermediate gear ratio. For our example, the intermediate gear ratios are 20 divided by 7 equals 2.9, and 30 divided by 2 equals 1.5. I want you to note and understand that neither of these are equal to the gear ratio for the entire train of 4.3. However, also note that 20 divided by 7 times 30 divided by 20 equals 4.3. So in general, the intermediate gear ratios of the gear train will multiply together to equal the overall gear ratio. So next we're going to talk about finding the rotational speed of our drive gears. So using the idea of gear ratios, it's easy to figure out how quickly a driven gear is rotating based on the input speed of the drive gear. To start, find the rotational speed of your drive gear. In most gear calculations, this is given in rotations per minute, or RPMs. For example, let's say that in this picture that we have a gear train that has a 7-tooth driver gear and a 30-tooth driven gear. The drive gear is rotating at 130 RPMs. With this information, we'll be able to figure out the speed of the driven gear. So the first step is we're going to be plugging our information into a formula. So the formula is going to be S1 times T1 equals S2 times T2. In this formula, S1 refers to the rotational speed of the drive gear. T1 refers to the teeth of the drive gear, and S2 and T2 to the speed and teeth of the driven gear. Often in these sorts of problems, you'll be solving for S2. Though it's perfectly possible to solve for any of the variables. In our example, plugging in the information we have, we get this: 130 RPMs times 7 equals S2 times 30. Finding your remaining variable is a matter of basic algebra. Simplify the rest of the equation and isolate the variable on one side of the equal sign, and you will have your answer. Don't forget to label it with the correct units. In our example, we can solve like this: 130 RPMs times 7 equals S2 times 30. 910 equals S2 times 30. 910 divided by 30 equals S2. S2 equals 30.33 RPMs. In other words, if the drive gear spins at 130 RPMs, the driven gear will spin at 30.33 RPMs. This makes sense since the driven gear is much bigger, it will spin much slower. Mechanical engineers use different gears that provide various ratios to transfer power through systems at different levels of torque and speed. Gearboxes are a common mechanical device used to change the torque, direction, or speed of rotating shafts. Gearboxes have a number of uses, such as wind turbines, farm equipment, washing machines, and many other industrial applications. Most often, the gearboxes slow down the speed of the shaft, which increases the amount of torque. Gearboxes have input and output shafts that are connected by a series of gears. The series of gears is known as a gear train. A gear train in which all of the gears are linked together in a row is known as a simple gear train. When pairs of gears are connected to each other on a common shaft, it's known as a compound gear train. Please take note of the graphics listed. Gearboxes are designed to have one gear ratio. However, it is often desirable to be able to change the gear ratio of a gearbox. This is the case with automobile transmissions. Manual and automatic transmissions that are used in automobiles are essentially complex gearboxes that allow for a change in gear ratio. Well, guys, this is the end of our lesson. So in conclusion, mechanical engineers must understand how to direct the correct amount of speed and torque to rotating parts in a mechanical system. To do this, understanding how to calculate gear ratio and speed are key. Mechanical engineers use different gears that provide various ratios to transfer power through systems at different levels of torque and speed. The applications can be simple or very complex, relying on combinations of all different principles discussed to design efficient and effective machines. These machines can range anywhere from a simple watch to robotic arms to automobile engines. I hope you guys enjoyed this video. Please get with your teacher if you have any questions, and have a great day.